right. Does everybody have a hard copy of the notes / practice problems? Does everybody have a calculator? And then if you would make sure that at least one person at your pod has their equation sheet. All right, so a little bit about this at the top we've already talked about. So things moving in a circle at a constant speed are not traveling at a constant velocity. This is because we've defined velocity to be both the magnitude and the direction of a speed. And so even if you're turning at a constant speed, you're still changing direction between every single piece of that circle. So what ends up happening is because we have a full change in direction, we also have to have some sort of acceleration. Because a long time ago, we defined our acceleration as our change in velocity divided by our change in time. So from here on out, anytime that something is moving in a circle, it is accelerating for some reason. Those reasons change. For example, in the lab that we did last time, that weird looking Newton guy was swinging a stopper around in a circle, right? What was keeping that stopper going in a circle? It was the string, right? Cut the string, you're not going in a circle anymore. And so in that case, that centripetal acceleration is from the force of tension. So the centripetal force is actually the tension force. So centripetal acceleration as a word is a lot like net force. It's not something that goes on the diagram and gets labeled as like F sub C. What it is it's tension that is also the centripetal force, or it's friction that is also the centripetal force. Or from the videos that you guys watched for last class period, when he was like rolling it around in the circle, that wooden hoop is providing a normal force that's keeping it in the circle. So the centripetal force isn't like a new force. It's just a new and very specific name for all the forces that we already know about. Does that make sense so far? So this second paragraph is everything that I just said, but the key piece is we don't really care about X and Y directions anymore when we're working in circles. What we care about are the in direction and the around direction. So if we look at this circle and let's say that this is just a toy car going in a circle on like a Hot Wheels track. Is that an acceptable? So what happens is from the top, a car kind of just looks like a block. And for Hot Wheels, the thing that's keeping it in the circle is like that edge of the Hot Wheels track, right? If you have a break in that edge, the Hot Wheel is just going to crash and burn in some different direction. So what we can label on that free body diagram is just, it's a normal force from the wall. But that normal force is what's keeping it going towards the center. So in this case, the normal force, Fn, is the centripetal force, Fc. And so what we're going to do is instead of defining like left and right and up and down as positive and negative, anything that's pointing in to the circle or towards the center is going to be positive. So all forces that point towards the center are considered positive. And so let's say for the sake of argument that instead of watching this Hot Wheel go in a circle that's flat or a horizontal circle, now we're going to make it do a loop-the-loop in a vertical circle. So it's kind of like if I look at this like this, the cart is going to, or the Hot Wheel is going to travel up and down, right? So then if I draw the actual free body diagram, at this point right here, we have a normal force that's kind of pointing in that direction, so towards the center. So this is our normal force. And then what's the other force that we have? From this perspective, we have gravity. And gravity will always point straight down when we're on Earth. So this is F sub G. The nice thing about doing problems like this in AP Physics 1 is that we only deal with basically like maximum, minimum, and things happening on the side. So right now, as this free body diagram is drawn, if I were to try to do Newton's second law, we'd have to do some weird trig to break one of these into components. We do not have to do that for any of these example problems, and you will not have to do that on either my test or the actual AP test. So let's label this position 1, and then let's label the top of this loop-the-loop as position 2. And so our free body diagram on position number 2, we still have the dot. We are still in contact with the track, hopefully. If you're not, this is the worst roller coaster ride of your life, and the last. So that normal force is now pointing down. But at the top of the loop, we still have force of gravity, and that is also pointing down. And so in this case, because both forces are pointing towards the center of the circle, both forces are positive. So it's no longer a question of up or down, it's into the circle or out of the circle. Does that kind of make sense so far? No, not for something like the normal force. Now, if your gravity force is not perpendicular, then what we'd have to do is break down the force of gravity into what would essentially be a negative component out of the circle. Yeah. So because we have a special thing for our force, centripetal force, we also have a new term for centripetal acceleration. And that equation is right here. This A sub c is equal to v squared over r. This is on your equation sheet. If I remember properly, it's in the far left-hand column, like a quarter of the way down, maybe. Yeah. So the rest of this unit, will you? Yeah, thank you. For the rest of this unit, anytime that we see acceleration, we just have to change it from being regular A to being A sub C. And so we're going to do some like warm-up conceptual examples first, and then we'll jump into the math part. First, think about a long time ago last semester when we went down to the Cross Connect and you had your meter stick and your marble and your golf ball and we were rolling them around. How did you get it to go in a circle? Where did you actually have to apply the force? You had to apply it to the outside. And you had to change the direction that you were applying that force, because otherwise you were just going to yeet it in one direction, right? So we've got a bowling ball that rolls down the hallway. We want to make the ball have a smooth circular turn to the right. So if we're currently moving forward, That arrow is the direction that I'm pushing the bowling ball. And then in order to get it to turn, if we want it to turn to the right, which side of the bowling ball do we have to apply our pushing force to? We have to apply it to the left. And you get your maximum value by pushing it 90 degrees to the right. Because you can't instantaneously change the motion of the bowling ball. It has to go through some piece of a curve. Now, if you wanted to go in a really like big circle, then you could apply your force at maybe like 45 degrees. And then that would be partially on the left side, but partially forward, so it would make it go in a large circle, rather than if you push it to the left, like directly to the left, in which case it's just going to go like, the plan for Friday was to actually go down to the Cross Connect and do this. So we'll do that when we get back. So in order to push the ball to make that turn happen, we're just pushing our force to the left side of the ball. So then while the ball's path is curving, are the forces on the ball balanced? Well, remember that when we're asking if forces are balanced, another way to ask that is the ball accelerating? And if we're changing direction, then we are accelerating. So the answer is no. The forces are not balanced. Because the ball is accelerating by changing direction. And the second part is to draw a free body diagram for the ball. So if we do this from like, I have weird examples. My brain is tired. I'm really sorry. But if we're like a little mouse that's following this ball, we're going to do our free body diagram from that perspective. So we're looking at the back of the ball, like eye level. So that means that we have our dot. We have the force of gravity that's pulling down on it. We have the normal force. And those two forces should be balanced because we're not accelerating into the floor and we're not accelerating off of the floor. But when we're accelerating in this right turn, we decided that we needed to apply the force to the left side of the ball, which means that force points to the right. And so this will be our force My handwriting is terrible. This is our force applied, F sub A. So you can go around in the circular argument of the forces are not balanced because it's changing direction, and we know by this free body diagram that the forces are not balanced, therefore it has to be accelerating. But the problem is this diagram doesn't tell us like what it's actually doing without context. Because this looks a whole lot like a person pushing a box to the right. So you have to have the context around it to know if it's going in a circle or whether it's going in a straight line. You will always have that context. So if we've got a car that enters a circular turn, we're going to draw a free body diagram of the car, or for the car, from a head-on perspective. So this car's about to hit you, so draw a free body diagram. You know, like you do. Yeah. Hold on, let me draw a free body diagram. All right. So our free body diagram, here's the car head on. So we've got the force of gravity that keeps it anchored to the earth. We've got the force normal that keeps it falling into the earth. Those should be parallel to each other. It doesn't say. Which way do you want it to turn? Turn right? So I'm going to add a note, turning right. All right. So if it's coming towards you, is it turning to your right or its right? So your left. So turning to its right. And so if you're seeing it come at you and it's going to turn to its right, that's our left. And so in order to keep it going in a circle rather than skidding right towards you, it's the friction that's keeping it in that circle. And so that means that it has to have a force here that is the force of friction. This is why, like, when it's icy outside or it's snowing or even when it's raining, like, you have to lower your speed. That comes from this equation right here. And it's because in order to make that turn, you have to have the right amount of friction rather than just like sliding straight off the curve. All right. If you're in a controlled spin, then you'll be fine. All right. So then lastly, as our warm-up, the International Space Station orbits the Earth once every 90 minutes. Why does the space station crash to Earth? Draw a free body diagram and also sketch the path of the station's orbit. So the short answer of why it doesn't crash to Earth is because it's really bad at aiming. And it's because it's moving at such a quick velocity that by the time it would be moving down, it's already like gone past that part of the Earth that it would crash on. And so there's a lot of like math and science that goes behind where this satellite needs to be in orbit, because the closer it is, the faster it needs to be moving to avoid that collision. So if we draw this picture, here's the Earth. And we're going to draw the satellite at a couple different spots. There's 1, 2, 3. We'll do it at 4 spots. At all points, what is the only force acting on this satellite? It's just gravity. And gravity always points towards the center of an object. And so the center of Earth is unfortunately probably like down here with the radius that I've drawn. So I'm going to draw all of my arrows towards this unfortunately placed point. So, yeah. So those are all the free body diagrams of that satellite. They're all the same. They just have one force, and it's the force of gravity. But what's changing is the direction of its velocity. Because here, its velocity is kind of that way. And then here, it's kind of that way. And then here, it's kind of that way. And here, that way. And so because your velocity is perpendicular to your radius, it's your tangential velocity. Which I don't know if you've talked about that in pre-cal, or I think it may have been mentioned in geometry, but I don't think it's a big thing. So Tangential is where if you have a spherical object, there's a line that intersects that sphere at only one point. And so if I move my pen across this, like the direction that the tip of the pen is pointing, that's the tangent, like that's the tangent to the circle. And so if we look at something that's in orbit, as it goes like this, the direction of my pen tip changes. This is where that change in direction comes from. Does that help a little bit as a visual? And so essentially the space station doesn't crash because it has bad aim. It's moving too fast to actually hit the Earth, because by the time it would hit the Earth, it's past that part of the curvature. This means that theoretically, if we shot a cannon off the top of our school building and we could shoot it at a high enough velocity and clear a path, it would come back behind us. Probable? No. Possible? Yes. It would be a very large velocity. But we could. But didn't we have another problem to solve first? Or was that a PoE problem that we were going to solve? I thought we had some big world-changing problem to solve. Nah. Clearly, it can't be that important. All right. So now for some of your favorite parts, so your not favorite parts, math. So we've got a 1,000 kilogram car traveling from point A to point B, rounding the turn of radius 70 meters with a constant speed of 17 meters per second. So this 1,000 kilograms is our mass. We've got a radius of 70 meters, and that's the radius that's going to go in the bottom of that new acceleration equation. How many of you guys have driven down Highway 16 recently? It's basically like if you take progress, like go past Walmart and then cross 412 and keep going and get to Fayetteville. Yeah. So that's my daily commute.
That sounds horrible.
It's not terrible.
My dad had to do it.
It is way less frustrating. I used to live in Bentonville and would have to come through the back roads and I have to go by the Walmart distribution center that's out there, and I would get stuck behind Walmart trucks all the time, and it was awful. But Highway 16 has some really interesting curves on it, because some of them you can take at 75 miles an hour, and some of them you can only take at like 40 miles an hour, and sometimes those curves are right next to each other. So what's changing though, the ones that you can take at larger speeds, they have a larger radius of curvature, which means that if I were to actually, give me a second, because this is kind of a fun experiment. Yeah.
Yeah, that's old.
All right, so Highway 16 is this curvy guy here. And so I can tell you my least favorite curve is this one right here. And the reason this is my least favorite curve is because it is an unbanked curve. And if you look at like Street View actually is less than helpful here.
That's true.
But if you,
my house has a photo from 2007.
I was showing my mother-in-law and my grandmother-in-law like the house that I grew up in Denver, and my grandmother-in-law goes, "Can you show me Truman from 1969?" And I was like, "No, that is not how Google Maps works. It is not a time machine." But anyway, this curve sucks a lot because you're going straight right here, and then you've got the sudden turn right here, and then you go straight again. So no matter what direction you're approaching it from, it's garbage. But if you look here, the turn starts like right about there, and then it gets straight again right about here. So if I made this whole thing into a circle, it would probably be that big-ish. As opposed to turns like this one on this side, you can see how much more of the curve we go through and how much larger the radius of this circle would be compared to this circle right here. So the larger your radius, the faster you can take that turn. Which is why the other turn that sucks is this one right here. The nice thing about this one, though, is that it's actually relatively wide when it comes to like how long you're in this turn, and so it's not as sudden. So if you ever want a good physics experiment, just drive Highway 16 to Fayetteville and you'll learn all sorts of things. And then you have guys like these that are basically just straight up 90-degree angles.
I really don't understand why we do that.
It's property lines. And it's which portions.
Push our road before the people.
How dare they?
Why can't it just be like, your land is mine? Road.
They do. That's called eminent domain, and that sucks a lot because they will never pay you the right price for your property ever. My mom in Denver lives like, if you walked too far out of her backyard, you'd end up on a major highway. That is now a 12-lane highway. And I am often concerned about her house being collected under like eminent domain. And then just being like, surprise, your backyard's now part of the highway. Which is super frustrating because there's a great show called Adam Ruins Everything, and if you haven't watched it, I would recommend it. It is sometimes very disappointing to learn that these like deeply held beliefs that you have about how the world works, that's not how it works. And I'm not talking about things like religion, I'm just talking about things like widening the highway and how it doesn't work, but nobody listens to the research, so we just keep doing it. Because.
Wait, what's the solution? Super faster? What if you can do that?
It's actually, so the problem, and the overarching problem is that the solution is to build the highway better the first time. Because the issue with traffic, and especially in places like Denver, are people trying to get on the highway and off the highway within a half a mile of each other. And so what you have to change is the infrastructure of how people get onto and off of the highway. But the price to do that at every on-ramp, again, in places like Denver, where there's one every half mile or every quarter mile, is absurd. And so widening a highway is like a band-aid to the solution rather than an actual cure for it. In order to cure it, we'd actually have to build our highways different the first time, but there aren't very many places where new highways are being built. We're really just modifying old ones. Other fun story, the first time I drove back here from Denver was when they changed what is now I-49. They changed it from, what was it, 430? No, it was, oh, this is awkward. Anyway, they actually changed the name of the highway. And so my husband and I got into Siloam Springs. It was like 11 o'clock at night. I was exhausted. It was technically 12 o'clock at night because you lose an hour coming from Denver. And all of a sudden we start seeing these signs for I-49. I was like, what the heck is I-49? Where are we? And it turns out that while we were gone, they changed the name of the highway. So that was cool. That's what I get for not reading newspapers. So I was to say, the wider your radius, the easier it is to take the curve. Back to actual physics.
No question.
Yeah.
What's your opinion on the new law on highways?
Which one?
Like, the left lane is only for passing?
I'm fine with that.
Okay.
Absolutely.
Yeah, you didn't know that?
It's been a law for a very long time.
It is. They actually enacted it like
well, what's
changed?
Yeah, what's changed is the enforcing of it.
Oh, yeah, you can stop.
It's a good call.
Yeah, but
If I didn't have to, I wouldn't.
the left lane is in,
Yeah,
Yes, it
I
was
should be,
nice.
because that's how,
Yeah.
if the left lane isn't only for passing, that's how you end up with, like, okay, the overall speed limit is 65 on 412, right? If the left lane isn't just for passing, that's how you get a guy in the right lane going 63 and a guy in the left lane going 64, and now it sucks for everybody. Whereas if the guy in the left lane goes 64 for a little bit to get in front of the guy that's going 63 and then moves back over, everybody else can pass both of those. But if the guy that's going 64 insists on staying in the left lane, then you're all stuck behind these two cars and there's nothing else you can do. Welcome to driver's ed with Miss Carter. So anyway, we've got this radius. That's what, coming back to the real point, when we say that it's a 70-meter radius curve, it means that if we were to turn all the road around it into a circle, it would be a circle with radius 70 meters. Does that help put that into context, what that looks like? Okay. And we've got a constant speed of 17 meters per second. So I am going to label that with a V. So for part A, what is the acceleration? Well, we have a fancy new equation where it's just our centripetal acceleration. And that's going to be V squared divided by R. We're told that our velocity is 17 and our radius is 70. And then I got 4.13. And it's an acceleration, so it's meters per second squared. And so even though we're going at a constant speed, we knew there was an acceleration because we're going in a circle. And that's the new key point, is being able to recognize that anytime that you're going in a circle, you are accelerating. And that acceleration is called centripetal acceleration. And so you use V squared over R. So then for part B, we're looking for the minimum coefficient of friction to keep the car from slipping. So what we're going to do here is we're going to use Newton's second law. Newton's second law was that the sum of our forces is equal to the mass times the acceleration. We've now seen the word force. That means that we need to draw a free body diagram. And so up here they've given you like a regular diagram for the rear view. So we've got a force normal that points up. We've got an equal and opposite force of gravity that points down. And then they give you this arrow to the center of the turn. And so this is the force of friction that's keeping us in that circle. Because without that force of friction, where's this car going? Straight. It's going, from the top down, he's turning left. And so when we look at Newton's second law and we look at the sum of the forces, we're going to do this in what we used to call the x direction, but in this case is the in direction. Because the force of friction is pointing into the circle. So the net force is in fact just the friction force. And all of that is equal to m times our new fancy acceleration, a sub c. And so if we go back to our equation sheet, the formula for the force of friction is mu times the force normal. And then I'm going to leave the m, a, c the same. And for better or worse, this is an unbanked curve, which means that our force normal is equal and opposite to our force of gravity. So instead of writing Fn right here, I'm going to write F sub g. And then we can break down Fg into its equation of m times g. And the nice thing is we're back on Earth, so it's our normal m times g instead of our gigantic equation. It's this mg part. On your equation sheet, on the bottom towards the right, there's an equation that says that little g is equal to the force of gravity divided by m. And so all we've done is multiply both sides by m. And so anywhere that we see Fg, we can just plug in m times g instead. Does that make sense? That's a good question. So this is equal to Mach. And from here we can start plugging numbers in. But the nice thing is what's on both sides already. Mass. And so if I divide the left side by m, because we're trying to get mu by itself, it cancels out. So we get mu times g is equal to a sub c. We're solving for mu, so I'm going to divide both sides by g. We found the centripetal acceleration in part A, so 4.13 divided by g, which in our nice little fictional world is 10, and we get 0.413. So I want to take a short break and look at this part of the equation right here. This mu is equal to AC divided by g. So the thing that you already know is that if it's icy out, that you have to slow down, because otherwise you're going to spin off. This is why, because the ice lowers the coefficient of friction. So in order to get a lower number on this side, unless I'm changing the planet that we're on, I have to lower the centripetal acceleration, right? But if we look at the centripetal acceleration, in order to make this lower, I can either increase the radius of the turn, but that requires me to apply lots of permits to the highway department and get them to change the road, or I can lower my speed. Not as fun, but probably more efficient in the long run and faster. So when it's icy out, mu goes down, which means a sub c has to go down, which means that v has to go down. And that's why you have to slow down when it gets icy. So, clarification, that's why you should slow down. You don't have to do anything in this life except accept the consequences of whatever you chose. Please don't die. All right, we're gonna do one more and then I'll stop talking at you. So we've got a 0.3 kilogram yo-yo. So this is our mass. On the end of a string goes around the world as it is cleverly revolved at a uniform speed of 4.15 meters per second. So that's our velocity. In a vertical circle of radius 85 centimeters. The first thing I noticed is that this is in centimeters. We don't use centimeters, we use meters. So R is equal to 0.85.
That's all I have.
Yep.
One's not affecting.
So part A asks us for the acceleration. Even though it is at a constant speed, it is going in a circle, so it's changing direction. So we can use our A sub C is equal to V squared over R. So 4.15 squared divided by 0.85. And I've got 20.26 meters per second squared. Part B asks for the tension in the string at the top. So in order to answer this question, we have to draw a free body diagram. And when we're at the top of this circle, we of course have the force of gravity acting downwards. So there's Fg. And then the other thing that's keeping this going in a circle is the tension of the string. So that's also going down. So this is Ft. So the sum of the forces, this is where we used to write it as like F1 plus F2 plus F3 plus dot dot dot. The only two forces we have are the force of gravity and the force of tension. And both of them are pointing into the circle. So both of them are positive. So I can write that the sum of the forces is equal to Fg plus Ft. Yes, sir. Yes, sir. The other equation is that we set this equal to m times a. But now we're all fancy like and going in circles, so this is going to be Mach. And we're solving for the force of tension. So instead of Fg, we can write m times g plus Ft is equal to mac. In this case, we cannot cancel out the masses because we've got this addition term right here. And so I'm just going to plug some numbers in. So the mass of this yo-yo is 0.3 kilograms. G is 10. Plus the force of tension, which is what we're solving for, is equal to mass, 0.3, times centrifugal acceleration, which we decided in part A was 20.26. Do some math, and I've got 3.08 newtons. So the difference in part C is now we're at the bottom. And so our setup is still the same, except when we draw our free body diagram, at the bottom of this circle, we still have the force of gravity pointing down. But now our force of tension is pointing up. Yeah.
Into the circle is positive.
Yes. Yep, into the circle is positive. So in part C, after we draw a diagram and we do the sum of our forces, Is it FT or FG pointing into the circle? This time it's FT. So FT is positive and FG is negative because FG is pointing out of the circle. And then all of this is still equal to Mach. So we can write FT minus MG is equal to Mach. So FT minus 0.3 times 10 is still equal to 0.3 times 20.26, and I ran out of room, sorry. And in this case, I've got our force of tension is 9.1 newtons, essentially. Right? And so if you look at it, it's because at the bottom of the circle, in order to keep it going in a circle, you have to oppose gravity. So your tension has to be higher. Whereas if we're at the top of the circle, the force of tension and the force of gravity are working together to keep it in a circle. So if this yo-yo rope is going to break, where is it going to break? It's going to break at the bottom. You can feel the same effect on roller coasters. If you're at the top of a loop, sometimes you feel weightless, and at the bottom it feels like something is smushing you into your seat. That's where this comes from. All right. There are lots more practice problems in here. What we would have done on Friday was do our little bowling ball experiment thing and then finish up the practice problems. So the practice problems are homework in as much as like we would have been doing them in class on Friday. I will post the answer key to them. The expectation is that you come back with this packet done when we get back from being remote, which is hopefully Tuesday. Correct. What we're going to do, though, now is bring this kind of back to the conceptual. Hey, Edward, I'm going to have you join these guys for this one. We're going to do this in 2 groups. I'm giving each group 2 baggies just in case you want to split them up. We were actually missing.
That's like 30%.
She's still a giant percentage of my class. I'm missing 1 person in my computer science class, which means we're missing 25% of our students. So that's been wild. Okay, in this card sort, there are not pairs. Like you're not looking for piles of things. You're looking to set this up into a grid with columns and rows that match each other.
How many?
I don't remember, honestly. But there are a couple different representations within the cards. Some of them are free body diagrams, some of them are just regular diagrams. I believe there are also some equations. I would like to note, there are some that look like this. This is a person that has tossed this ball in a projectile this way. So it's not in. It means that that's the tangential velocity at that moment. So it's not in contact with their hand anymore. And then in some of them, they do try to give an indication of the ceiling. So like anytime you have a line like this, that means that this thing is hanging from the ceiling and is attached to a string of some sort. So if you need help with orientation, let me know. I've given you guys 2 sets of cards at each table. Really, it's just like the 4 of you guys are working in a group and the 3 of you guys are working in a group. But if you wanted to be able to see what else was in there at the same time, I gave you an extra. Make sense? Alright. We'll go over it before we leave. It's the beginning of rocket science.